Output value. Okay, good morning, everyone. How did the homework go? Please put on chat if you have any questions from the homework. Okay, are you guys comfortable with the material then? Okay, I'll give you 1 more minute to see if you have any questions before I proceed. Okay. All right, so today we're gonna, if you have no questions, we can still have 2 ideas to talk about 1 idea actually about the conic sections, and then we proceed to parametric curve. The conic sections, so far we saw first equation of a circle centered at any point hk, and the equation of a circle has the form x minus h squared plus y minus k squared equal to the radius squared. So here the center is hk and the radius is r. So that's for the circle. And then we saw the ellipse. We saw the standard form of the ellipse. It means x squared over a squared plus y squared over b squared equal to 1. And we split this into 2 scenarios, a larger than b, a smaller than b. And if a is larger than b, it was elongated horizontally. That's the a, the minus a. That's the b. And the foci were here. For a less than b, it was elongated vertically. These are the vertices, and these are the a. So always this is the b, and this is the a. And then we shifted them, and when we shift, the only thing that changes, the equation, everything remained the same, but the equation is slightly different. Instead of x, we have x minus h. And finally, we saw the hyperbola. And for the hyperbola, we have the following equations. First of all, what separates them is the minus. So it is x squared over a square minus that. And in this case, my hyperbola is basically opened left and right. there is no y-intercept, but the x-intercept occur at A, right there, and this is minus A, and this is A. And the asymptote were plus or minus B over AX, those famous asymptotes. The other equation of the hyperbola, when it is going to be going up and down, what matters is not whether A bigger than B, A less than B. It doesn't matter for the hyperbola. It's what we start with. So it's y squared over B squared minus x squared over A squared equal to 1. The equation of the asymptote remained the same, but the difference in this scenario is that they were open up and down. So that's really the summary. And then we shifted them the same way we shifted the others. So the idea we're going to talk about today is that sometimes the conic sections come in a form that, you know, I call them in disguise. It means they don't come in this nice format. The reason is if you take an equation like this and you do the following, you actually distribute x minus h squared and y minus k squared, and you distribute, it's going to have something like that. It's going to have a form like x squared, let's see, minus 2hx plus h squared. So it's going to have like some kind of a quadratic form. And whatever. So minus 2yk plus k squared over b squared equal to 1. So when you distribute, it's going to have the form of what we call a quadratic equation. So the question now is, if the equation is giving you this way, how you go back to that format and realize that you have an ellipse? So this is really what we are going to work on it at the beginning today. And it's actually simple. So let me take the following equations. So it doesn't look like a hyperbola. It doesn't look like an ellipse. It doesn't look like a circle. It's what we call a quadratic equation in x and y. Quadratic, it means the highest power of x is 2 and the highest power of y is 2. So it's quadratic in x and y. So let me take the following equation. Minus 8y equal to 0. That's what we call quadratic equation. Now at the surface of it, I don't know whether it's an ellipse or a hyperbola or even a parabola or a circle. I don't know anything. And even if I can recognize what it is, I don't know what the center, what the vertex is. And the question is, okay, you have to identify this as one of the conic section. And whatever the conic section you end up with, I want you to find what characterizes this conic section. So if it is a hyperbola, I want asymptote, foci, vertices. Ellipse, I want the center, of course, the foci, the vertices, and so on and so forth. So how do we handle those type of problems? The idea is I want to kind of rewrite them. I'm going to really go backward. I'm going to try to rewrite them in this form, or in that form, or in that form. So I want to go back from here all the way. And how do we go back? That's where completing the square idea come into the picture. So what do I mean by completing the square? X squared is going to remain the same. Now, let us remember, how do we complete the square in general? If you have something like x squared plus bx, the coefficient of x is 1. And this algorithm works if this is 1. Remember, how do we complete the square? That was the idea. We take the coefficient of x, which is coefficient of x divided by 2, squared, added, and subtracted. That's really the algorithm. And by doing this, this will be a complete square minus this term we will deal with it. And this algorithm works as long as the coefficient of x squared is 1. So I want to complete the square for this piece. Here there is nothing. X squared, it comes by itself. So the first step I'm going to do is factor out the 4 So I can use my algorithm. I factor it out. I will have y squared minus 2y. Okay? Now I want to complete the square within this piece. So I'm going to open my parentheses. It's y squared minus 2y. Now we know how to complete it. We take the coefficient of y, which is a 2, minus 2, divided by 2, added and subtracted. So this by 2, it's like 1. So square it, 1, added, subtracted. So the idea is to go backward, is to go exactly to the shape, to the form, the standard form of conic section. So this will give me the following. This piece right there is the y minus 1 square. And this is that. So we're almost at the end of that. So this is going to give me, now I'm going to distribute the 4. Minus 4 equal to 0. So the goal is really to go back to our format. And now this is actually, now at the end, it's x squared plus 4 times y minus 1 squared, this minus 4. And we can already recognize what conic section do we have, right? What conic section do we have now? Ellipse, circle, hyperbola quickly. And what's the character, what characterizes this? And we're going to sketch it. So what's this? Quickly. What shape are we going to have? Plus, we're going to have an ellipse. So to be able to find the vertices, foci, I need to rewrite in standard format. So in standard form, I need to divide by 4. And this will give me that. So as you realize, you were able to go back to something that's a 1 equal to 1. Where is my eraser? There. Equal to 1. So definitely I have an ellipse. There is no question about it. And now we will sketch the ellipse and figure out what characterizes it. So first I will, the center is a 0 here, and it's a 1. That's my center. In this problem, A, this is the A square. It means my A is 1. And this is the B square. It means, so my A is 2. And that's the B square. It means my B is equal to 1. So A bigger than B, it means it's going to be elongated horizontally. And I get started with the graph here. So the center is 0, 1. This is 0, 1. So this is my ellipse centered here. And because A is bigger than 2, everything A is bigger than B, it means the foci, the vertices will be on the line which is parallel to the x-axis. A is 2. That's my A. B is 1. This is my B. So I'm going to have this kind of ellipse. That's the ellipse. So we can really draw it immediately. That's 1. So this is the B. This is the B, which is a 1, and this is the A. So the foci are easy now. The vertices are just, we look at them. If this is 2, these are the vertices. And this axis is what we call the major axis. That's the major. And the one perpendicular to it, sometimes we call it the minor axis. So the vertices are easy. So we have the vertex right here. It's a 2 and a 1. And the vertices here are -2 and a 1. And for the foci, I need the c square. The c square is always, for ellipse, is a squared -1, which is equal to 3. So immediately, they are 1, that's the coordinate, and they will be right there, plus or minus the square root of 3. Okay, so that's really the idea of, if the conic section is not given to you in the standard form, basically, this can come as a disguise as a quadratic equation. and we move backward to be able to write it in the way that we would like it to do. I'll work out one more problem along those lines, and then we move on. So my second problem, which is, you guys should be comfortable with that at this stage. So 9x squared minus 36x minus 4y squared plus 32y equal to 64. So it looks really complicated, but it's not. And my question is, identify this immediately as a parabola, hyperbola, circle, or ellipse, and find everything. So how we are going to do that? Okay, we put all the axes together and we try to combine them somehow to complete square, and we do the same things for the y. So to complete the square, as I said a minute ago, we have our algorithm work as long as the coefficient of x squared is 1. So my first step would be to factor out the 9 in here. The algorithm work when the coefficient of y squared is 1. So to be on the safe side, I factor out the 4. 64 is my constant term. I don't touch it for now. So that should be the beginning. After that, it's really systematic. We complete the square, and 32 over minus 4, that's going to give me a minus 8y. So we watch the algebra very carefully. Now we complete the square and we finalize. So this will give me 9 times x squared minus 36x. Let us remember how to complete the square. Coefficient of x is 32. Sorry. No, I did a stupid mistake here. You guys tell me when I do mistakes. 36 into 9, it's a 4 in here. So minus 4x. The coefficient of x divided by 2, it's a 4. Square it, add it, subtract it, minus 4 times. I'll do the same here. Coefficient of y is minus 8 divided by 2 minus 4. Square it, add it, equal 64. So we do it very slowly, and then the rest is simple. Now the first terms, those will give me my first complete square. Minus 4. Minus 4 times, this gives me my second complete square. This would be y minus 4 squared. And minus 16 equal to 64. So we collected the x together and we collected the y together. Now I'm going to distribute those constants and write it in the format I want. So this will become 9 times this minus 36 minus 4 times y minus 4 squared minus plus 64 equal to 64. And as we realize, it looked like absolutely impossible to know what we're talking about at this stage. By manipulating it, we are going to be able to figure out all the points which lies on the first curve. So the 64 cancel. So this will give me 9 times x minus 2 squared minus 4. Now I'm writing it in its standard format as a hyperbola. Of course, the minute we see the minus, we know that we have a hyperbola. I want to write into standard format. I have to divide by 36, and I do the math. 9 over 36 would leave me with a 4 minus y minus 4 squared. 4 over 36 would leave me with a 9 equal to 1. So obviously now we know that we have a hyperbola. And this is a minus here. It means the hyperbola will be left and right because the x is coming ahead of the y. So it's a hyperbola. And what characterizes a hyperbola? We need the intercept, and we need the asymptote, and we need the center, of course. and we need the foci. So the center is easy to pick up. It's going to be 2 and 4. And immediately I start building up my hyperbola. So it's a hyperbola centered at 2, 4. So this is a 2. And this is my 4, kind of. So that's going to be, will be the center of the hyperbola. And what I know is that because x squared comes first, the one that has a plus in here, so I have a in the scenario is equal to 2. So that's the a squared. So the intercept will happen here. That's a equal to 2. And this is a equal to 2. So basically it will look like that. It will look like this. Because this hyperbola is nothing more than the following hyperbola shifted. So it's the hyperbola x squared over 4 plus y squared over 9 shifted. So it's going to be shifted 2 units to the right and 4 units up. So the center now is right there. So it's really a shifted hyperbola, 2 to the right and 4 up. And that's how the center is going to become the 2 and the 4. So that's why it's a shifted hyperbola. So the vertices now will be. This is what we call the vertices for the hyperbola. So this will be 4 is the second coordinate. This is 2 because that's the center. A is 2, so it will be 4, 4. And this point right here, which is going to be 0, 4. So those are easy. The foci will be inside here. So the c squared for the hyperbola is the sum. So the foci will have for coordinate the following. The c is from here to here. That's the c, which is the square root of 13. So there will be 2. That's the 2. Add square root of 13 and then take away the plus or minus the square root of 13. And the y coordinate is 4. Finally, the asymptotes, which sometimes give us hard time, but they shouldn't. What are the asymptotes? As I said yesterday, the asymptote this time go through the center, 2, 4. So this would be a point on the hyperbola. Sorry, a point on the asymptote. So for the asymptote, we need, it's a line. We need a point and the slope. The point, the standard one, the one centered at the origin, the hyperbola, the asymptote go through the origin. But when everything is shifted, then the asymptote will have to go through the point 2, 4, the center, the new center. So that's a point on the hyperbola. Now for the slope, the standard one, the one which is centered at the origin, we have 2 slopes. This is b over a, that's the slope here. And this one, the slope is minus b over a. When we shift so that the center is to 4, the slope are not going to change because they are parallel to those. So the slopes, we have 2 of them, depending on the line. One is the b over a, that's the slope. And my b is 3 in this problem. My a is 2. And the other one is minus b over a, which is minus 3/2. So those are the slope. So the equation, we will use the point slope for y minus 4, that's the y, is 3/2 x minus 2. And the other one is almost the same, but it's minus 3/2 x minus 2. Okay. So this part we've seen yesterday, but the new part here is basically that sometimes you have a quadratic equation. It means an equation. When I say quadratic equation, I mean an equation where the highest power of x is like, the highest power of x is 2, the highest power of y is 2. So sometimes we have a quadratic equation like this, and you would like to know, well, whether this will generate, what type of conic section it will generate. And the only way we can go around this is basically by completing the square and rewriting it in a more standard format. Once it's in our standard format, we know the shape of those type of curves. Okay. Any questions before I move on to our new topic of today? All right. I hope you guys are doing the homework. I cannot check you. I'm just relying on you not asking me questions. Okay, today we're gonna back up to section 10.1 and parametric curve. So what is the idea of the parametric curve? So 10.1 parametric curve. Now, of course, you guys have all the lecture note on Blackboard. So the idea is the following. Suppose I have a curve. Now, what is really a curve? I mean, I use this word a lot. So this is a curve. This is a curve. That's what I mean by a curve. As simple as that. So we call this a curve. Okay. Now, suppose I want to describe this curve for you. I want to describe this curve. Okay, so I want to give you a way or a formula so that when quote unquote you graph this formula, you get a shape like that. So what is the difficulty in giving you a formula for this curve? Difficulty number one, is it possible to give you the formula of the form y equal f of x? Yes or no? I'm expecting answers. No, and a big no. Because why? There is no way this could be the graph of a function. Because you remember, for a function, every value of x should give you one value of y. And there is no way to do that here. If I give you this vector of a value of x, all right, there are three different values of y. So I cannot describe this curve by giving qy as a function of x. So we will describe this curve in a different way. So we are going to describe it in the following way. And to make the way we are going to describe this curve a little bit intuitive, we usually talk about the following scenario. Let us assume you have an object like, a small particle, you can imagine an ant or something, moving along this curve. So you imagine you have an object moving along this curve. Okay, so at every time, so there is a time in the background. At every moment in time, the object is somewhere on this curve. So it's move and move and move and move and move. Okay, so imagine the following scenario. And suppose I tell you that for every time, I give you the following. For every time, I tell you where the x coordinate of the object is, sorry. So I do the following. For every time t, I will give you two things. I will tell you where the x coordinate of the particle is. So I give you the x coordinate, and I give you the y coordinate. So suppose I give you two equations. One that gives you the x coordinate and one that gives you the y coordinate. And for every time I tell you, for t equal to 0, let us say, I give you the x and y coordinate of the object. At t equal to 1, I give you the y and x coordinate. At t equal to 2, I give you the x and y coordinate. And for every moment in time, I give you a formula that will allow you to find the x and y coordinate. So I give you two functions, f, which tell you what the x coordinate is, and I give you g, that tell you where the y coordinate is. So if I do that for every moment in time, I give you two formulas. One that tells me what is the x coordinate, one that tells me y coordinate. Then as time goes by, I will be able to trace the whole curve. So what's a good way of describing this curve for you? I cannot give it y equal function of x. I will introduce a parameter t, which intuitively think of it as a time. And I'll tell you where is my object at every moment in time. But how do I tell you where is my object? I tell you where the x coordinate, what's the x coordinate is as a function of time, and what the y coordinate is as a function of time. If I do that, then you will be able to trace the curve. So that's what we call parametric curve. Parametric curves are curves, which are something like that, where it's given to you by the following way. For every t, which is I want you to think about it as time, I tell you what the x and y coordinate is. By doing this, I can actually describe the curve for you. So that's what a parametric curve is. So a parametric curve is a curve where involves two equations, involves a parameter t, and it involves two equations. One that tells you where the x coordinate is at every moment in time, and another one that tells you where the y coordinate is. Those two equations are called parametric equation of the curve. So instead of giving you x as function of y function of x, because I can't, I give you both of them as a function of a parameter t. And those are called the parametric equation of the curve. And when a curve is given this way, in terms of a parameter, not as y equal f of x, we call this a parametric curve. It means it's a curve where both coordinates are given in terms of a third parameter t. So that's the idea of parametric curve, which are absolutely used tremendously because things don't have always to follow the graph of a function. Now let us work out with some example, which will not be hard. So the idea is very interesting, very important, but the examples are actually not very hard. So let me start with my first example. So let's consider the curve, which is given by the following parametric equation. So x equal, let me type it, and y equal, let us say, t plus 1. So I will consider a curve which is given by those two equations. So question number one is the following. We're going to try to somehow understand that. I would like to sketch the curve that's given by this equation. So how do I sketch it? This equation tells me for every t, what's the x and what's the y. So to sketch this curve, I will do the following. I have a parameter t. As t vary, the x and the y component vary. So I'm going to have the x, So we'll do it really in the most basic way. This is the x and this is the y. So x is t squared, y equal t plus 1. And right here, I will describe the curve. So what does this mean? I will skip the negative value for a moment. It means at t equal to 0, so imagine this is an object moving. At t equal to 0, what is the object? Its x coordinate is 0 because it's t squared. Its y coordinate is 1. So now, every time I find something, I find a point, I will graph. It means at t equal to 0, my object is, its x coordinate is 0, its y coordinate is 1. So this is where, if you think of it as an object moving, this is where the object starts. I'm going to jump. After t equal to 1, where is the object? Its x coordinate is 1. Its y coordinate, I plug in 1 in here, so it's 1 plus 1. This is equal to 2. Means after 1 unit of time, my object is at the x is 1 and the y is 2. So that's where my object is, right there. So that's at t equal to 1. That's where I am at. So that's the point, which is 1 and 2. Yeah, I keep at 2. Of course, you're not going to take every possible value. We just take few values, just like when you sketch a function. At 2, my x is at 4, because that's where the x coordinate of the object, and my y is at 3. So for t equal to 2, 1, 2, 3, 4, and this is a 3, which should be right there. So this is at t equal 2, my object is right there. Now a very simple question. Is x going, so intuitively, assume t positive, as t increases, obviously the x coordinate is going to increase and the y coordinate increases. So as time passes by, x coordinate increases, it means the object moving to the right, and the y coordinate is increasing. It's 2 plus 1. It means the y tells me that the object is moving up or down. If y is increasing, it means the object is moving up. So what's going to be the motion of the object? Is going to go like that. That's how it is moving. So we know exactly its direction of motion. Now I took here t positive to emphasize, to help us with the intuition. But in general, t will be allowed to be negative. So we're going to take a bunch of negative values and see how the curve look like. So I will take -2 and -1 to help me figure it out. At -2, the x is the quantity that is 4, and y -2 plus 1, -2 plus 1, it is a -1. At -1, x is 1, and the y is 0. So let's do that. So at -2, at t equal -2, my x is 4, my y is -1. So this is -1. So my object is right here. T equal -2. So I have the 4.4 -1. And t equal -1, my object is right here. So in between, what's happening? What's happening between -2 and 0? As t is increasing, -2, -1, 0, the y is increasing. So the y increasing, it means as t increases, that's the way I think about it. As t increases, if the y increases, it means my object is moving up. Now, when t is negative, I have here t squared. The x decreases. So -2, 4, -1, 1, because it's a square term. So when t go from -2 to 0, my x decreases. If the x coordinate decreases, it means my object is moving to the left. So up here, my object is going up, but moving to the left. And this really gives me this type of curve. And the object is moving that way, that way, that way. So that's really the curve we get. So we know the direction of motion if you want. The arrow tells me how things are moving. And this is the shape of the object. And that's the curve. Okay. Question 2, that's a lot of time, not a lot of time, that sometimes we can answer and sometimes we can't, is the following. If we look at this graph, at this curve, so this is my curve C, that's the curve. And your calculator can sketch them. A lot of every algebra system, computer algebra system can sketch those curves. So, but the second question is, the shape looks like parabola. Am I right? Does it look like a parabola? So the second question that it's useful sometimes because it's doable and sometimes it's not doable is the following. Can you find an equation that relates every point x and y on the curve, which does not depend on t. So the question is B. This is the curve. I'm done. But sometimes we ask, can I find an equation that relates the x and the y that hold regardless what t is? So can I, okay, everybody is telling me x is y minus 1 square, and Philip is correct. So let us see, what's the relationship? So x is t squared, and y is t plus 1. So this is a question that we will answer when it's doable, and we can't answer sometimes. And of course, I will let you know when we can't answer this question. So the question, can I find a relationship between x and y that hold regardless what t is? And now the idea is, no matter what t is, I'm going to solve for it here. T is always y minus 1. So I will eliminate t from here, and then say, so no matter what t is always y minus 1. So I will plug it back into x. Means x is by minus 1 squared. Means for every moment in time, my x, that's the equation that's going to relate the x and the y. And this equation, if we draw it, it's basically y squared shifted up by 1 unit, which is y minus 1 squared. All right. So the equation, the Cartesian equation of this is x equal y minus 1 squared. That's the Cartesian equation. And because, as I said, I can do it. Sometimes I can't. But you can ask me the following question now. So why did you go through this trouble if you can express this curve by this equation? For this problem, my answer would be, this equation will tell me only the shape of the curve, that it looks like this. But if I want to think of this curve as an object moving along it, this equation will not do the job. However, those equations are actually telling me that the direction of motion. If you think of this as direction of motion, the parametric equation tells me the position of my object at every moment in time. And more likely in calculus 3, this parametric equation will also tells me how fast is the object moving with respect to time. And you guys will talk more about this idea in calculus 3. So because it's expressing x and y in terms of time, is going to give me actually a lot of info about the speed of the object with respect to time, the direction of motion, and eventually this will be a better representation of the curve than this one would be. So this tells you in a static way what's the shape, but it doesn't really give you what's the motion itself of the curve. Okay, we will do now another, hopefully 2 more problems along the same lines. Very basic problems. So my second example, one of the most basic, famous examples for parametric curve. I'll try to do 2 of them. So example number 2 is the following. So before I go on, so how do we eliminate parameter? It means how do I find the Cartesian equation? Usually one way to do it is you try to find a relationship between x and y that doesn't depend on t. So there are several approaches. One approach is you solve for t in one of your equations and you plug it into the second one. And you pick the one which is the easiest to solve for. Example number 2 is, these are my parametric. I don't know, I'm going to put sine of t here. And for y, I will put the cosine. Actually, let's put 4 sine, a little bit more, and 4 cosine. And this time, I will put condition on t. So I want t to be between 0 and 2 pi, just to make the computation a little bit easier. And my question is, so how do you think about this? You have a particle which is moving. At every moment in time, its x coordinate is given by this equation. and its y coordinate is given by this equation. If you think of the problem this way, then those parametric equations start making sense to you. So they will not be abstract anymore. So I want to sketch the motion of this particle. So I have here my x and y axis, and I want to sketch it. The only way I know how to sketch the motion, what's going on, is by taking values. So I ask myself, as t move, what's going on? So I need to find the x is the x coordinate is 4 sine t, and my y coordinate is 4 cosine t. And I'm only interested for t between 0 and 2 pi. Now, what benefit does seeing the movement of an object of this parametric function have? Because you will study parametric, because parametric curve will be a lot of time used to you to actually describe how an object is moving. That's exactly how, yes, it will describe. So a lot of time you will have enough in physics, in a lot of your courses, you have an object which is moving. And then they have to describe it to you. One way they can describe it to you is basically by giving you the parametric equation. And through them, you will know how the object is moving. That's really the importance, because they are used to describe motion in the plane or motion in R3. So they are used for doing those things. So let me describe this curve. So initially, I have to take values of t. Now, because it's t between 0 and 2 pi, and because I'm computing a sine and cosine, will it be smart to take t equal 1? What do you think? Yes? So you go figure out for sine of 1. I don't, because I don't know it. So which, yeah, so because I really don't. I'm trying to do with what I know. So it's very easy. As the unit circle, yes. Not unit circle, Sarah, you're almost there. All right. So what will be your second thought, Phillips, instead of 1? Yeah, values of pi over 2, because we can really control them. Anyway, let's do that. If x t equal to 0, 4 sine 0, let me actually add here the graph of sine and cosine, because I like those graphs and you should like them too. So that's the sine and that's the cosine. The sines, I'm only in the sine. So these are the graph of sine and cosine because we're going to use their values a lot. And that's my cosine. So at t equal to 0, the sine is 0. The cosine is 4 times cosine of 0. Cosine of 0 is 1. So this is going to be equal to 4. So at t equal to 0, my graph is right there. I am right here. Now I will take pi over 2 because, you know, those are nice values. Cosine pi or sine pi over 2 is a 1. That's a 4. And for cosine t, cosine pi over 2 is 0. That's a 0. And for t equal pi over 2, I am at 4, 0. I'm right here. Okay. I will take those values. But before I take those values, I want you to think a little bit with me. As time increases between 0 and pi over 2, what happened to the x coordinate of the particle? So imagine this particle moving according to this formula. There is a reason I put the graph of sine in front of you. So as time go between 0 and pi over 2, what happened to the x coordinate? Is it going to increase or decrease? I want an answer. Increases, it increases because as t go from 0 to pi over 2, the sine, which is the x coordinate, is actually increasing, which tells me that as t moves, the x coordinate increases. At 0, the x coordinate is 0. It means we're going to move to the right. So we're moving to the right between 0 and pi over 2. This helps us a little bit intuitively. What about the y-coordinate? It's 4 cosine t. That's the graph of cosine. And that's my pi over 2. 4 times cosine, multiplied by 4. It's not going to affect really increasing or decreasing. Between 0 and pi over 2, the cosine decrease. It means the y-coordinate will decrease. So we're starting here. It's decreasing. It means we're going to the right and we're going down. So basically, we're moving this way. So this analysis is simple, but really help us to understand the picture better. Now I keep going along the same line. Between pi over 2, my second good value is a pi. Sine pi is a 0. Cosine pi is -1 times a 4, which is a -4. So at t equal to pi, I am t equal to pi, t equal to pi, I am at 0, and -4, I am right here. And in between, what's the curve? Now we know that's going to do like that. I mean, we expect that. But again, I will analyze it. Between pi over 2 and pi, why this is a correct motion? Between pi over 2 and pi over 2, I am right here. Between pi over 2 and pi, the x-coordinate is getting less. If the x-coordinate is changing, it means I'm moving to the left because it's decreasing. Between pi over 2 and pi, the y-coordinate is actually keep on decreasing and getting less and less negative. It means we're still going down and down. So we're moving to the left and we're moving down. That's the motion of my particle. And then I can keep along the same line and it's gonna go like that. So I know that my particle now is moving along this curve and it's moving in clockwise direction. So now this is following those parametric equation. I will get a particle which is moving on this curve that Sarah told me it's a circle that she's right, but we're gonna figure it out in a moment. So it's moving on the circle and it's moving in the clockwise direction. If I play with those a little bit, I can let it move in the counterclockwise direction. So, but this scenario will move it in the clockwise direction. Now, question number 2 is, of course, we all realize that it looks like a circle. Now, my question to you is actually why it is a circle. How can you convince me that it's actually, I may have goofed a little bit somehow. How can you convince me that it's actually a circle? Meaning, I want you to eliminate the t and find a Cartesian equation that relates the x and the y. So number 2 is eliminate the t and find is Cartesian equation that relate the x and the y. So who would like to give me this? I remind you what I did in the previous problem, but I cannot imitate it all the time. In the previous problem, I had a simpler scenario. So in the previous problem that I cannot find the paper for it, divide by 4 and square and use a trig identity. You guys are absolutely correct. So here in the previous problem, because I have to connect the dot, I had x equal t squared and y equal t plus 1. In this scenario, it was easy to isolate the t from here, expressed in terms of y, and then plug it back here. So that was actually a simple scenario that you're going to do a lot along that for tomorrow. Right here, it's kind of hard because I cannot isolate my t. It's a nightmare. But I know this famous relationship between the sine and cosine. And that's exactly what I'm going to tap into. So from here, as your classmate said, divide by 4. This will give me x over 4 is the sine of t. And this will give me y over 4 is the cosine of t. And now I'm going to tap into the trig identity, which tells me that the sine square plus the cosine square of t equal to 1. And this will give me x over 4, the whole thing squared, plus y over 4, the whole thing squared, equal to 1. Now we want to see it a circle, but this doesn't quite look like a circle, but we can make it up. So it gives me x squared over 16 plus y squared over 16 equal to 1. Now this looks like an ellipse, but a special type of ellipse. Ellipse when the A and the B are equal. And an ellipse where A and the B are equal is basically a circle. So if I multiply by 16 across the board here, I will get x squared plus y squared equals 60. And that's definitely will give me a circle centered at the origin. And the radius is, this is the radius squared, and the radius is equal to 4. So we had a hunch it's going to be a circle, but now I know exactly that it is a circle because I know the relationship between any point here. So I take any point here. If this point satisfies those two equations, then the relationship, the equation that relate those points is x squared plus y squared equal to 4. And this is this parametric curve, or given by this parametric equation, really describe a motion along a circle. And the motion is in the, as I said, in the clockwise direction. Okay. Now I can start like playing with this curve a little bit, and probably some of the homework that like I can put a minus in here. How will this affect the motion? Will it affect the motion? Do you think it's going to affect the motion? Absolutely. It will not affect the curve. It will be always a circle. But it's going to totally affect the motion right there, because what's going to happen here is the starting point will be totally different. So instead of 4, it's going to be a minus 4. And this would be a plus 4. So this will basically be an object that's going to start moving from here. And so 0, minus 4, and then it's going to go to 4, 0. So it's actually going to do, it's going to move in the counterclockwise direction starting from here. So a little change in the equation will not basically change the physical curve, but it will change how your object is moving along the curve. Think about it. That's a good question. Think about it. And put a minus here and see how will things be affected. You will start from here, but since you got minus, it means look what's going to happen according to the curve. That's what will happen. That's the minus. So between 0 and pi over 2, the x coordinate is going to be negative. So if I'm drawing it here, right here, I draw the curve, we will start right there. Between 0 and pi over 2, my x coordinate is going to be negative and it's decreasing. So the curve will start here, but it's going to move that way. Okay? That's way. That's going to be the motion. It's going to be opposite to what this one is. Make sense? Okay, so that's the importance of really, really caring about the motion itself. So the curve will be a circle, but it's how the object's moving along the curve, which is really important when you put this parametric equation. Okay, any other questions beside that? Now I want to ask you a question. I want you to be honest about it. Are you doing the problems about integration? Yes or no? Please do. If you have questions, I'm going to answer you. That's my only way to help you get ready for the final. All right, that's the only way. I mean, usually when I have a regular class, by now I will be quizzing them every day on this stuff. So I may do that tomorrow. I may do that tomorrow. I may give you a pop-up quiz tomorrow. on integration. I want to make sure that you guys can do both. I mean, remember your integration techniques and learn the new material, which is absolutely important, as you realize. Okay, any questions before I let you go? All right, please, if you have, as usual, I repeat myself, meet me in my Zoom office hours if you have questions. Very few of you are coming. Please feel comfortable to come. Okay, and bye for now.